features about the eye that these techniques are measuring simultaneously, and they're saying, okay, if this color is redder than that, and there's a vein in that area, and this thing is yellower than this amount, and so on and so forth, they're combining all of those things into a single estimate pretty much instantaneously. And this obviously has very, very good real world effects. And we're seeing this kind of thing in many, many different areas. Now, that's just sort of applying CS, right? I want to go even deeper than that. So these are just some random, top X colleges picked from across the world. And you'll see that all of them have a bunch of courses, and these are all very heavily attended courses in what one might call, loosely speaking, CS plus X. But that sort of almost creates a separated CS plus X, as if these two are two separate things. But I already argued, in some sense, about how CS is not really a subject of its own. It's more pervasive than that. It's almost like math. No matter what you're studying, math can help you do it better. CS can help you do it better and earn money while you're at it, as I see it. Now, the first half, as I said, was CS not being a single subject. Now I want to say that plus X, it's not outside of CS. It's deeply integrated. It's you can't silo it away, right? It's about taking the processes that you use when you're looking at journalism, let's say, and trying to apply computational thinking to it. Because one might say, oh, looking at the media, there's a lot of polarization in there. CS says, okay, how do we measure it? Can we see how a single article might change the polarization of people who are reading it? How would we do that, right? Is there a deeper way to look at the data? Is there a better way to process and gain insight from it? And what can we do from that point on? And that's actually a real project that's being turned into a startup, honestly. So real stuff. Now, at Ashoka, when we're talking about CS plus X, there's a couple of basic advantages that I want to point out. Number one, we have a lot of very talented people across multiple disciplines. I'm not going to drop names, but the idea is that these are people who are very much at the top of their fields, and there's a certain effect that this has whenever one is attacking problems. When you're around good people, you tend to be more productive yourself, right? And we've been seeing some of that at Ashoka when it comes to the kind of research we've been doing at these sort of in-between disciplines, these cross-disciplinary areas. So I'm going to focus in on some of them, but towards the end, I'll also talk a little bit about core CS research, because I think that's also important. That's sort of the foundation on which all of this is standing. As such, I think, given that most of your students, you're probably interested in the coursework. So we have a lot of really, really cool courses. Let me see. I mean, the usual blockchain stuff is there. You'll see that at a bunch of places, but I can tell you definitely, and I'm sure Archit will back me up on this, we have a phenomenally cool blockchain course. Like, you actually learn how to use and deploy blockchains. It's not just some theoretical thing that you're reading about, right? We have a number of excellent interdisciplinary courses. I teach one called The New Geography of the Information Age, which is a lot of fun. We basically look at the interface between society and tech, trying to figure out sort of at a civilizational level, how to realign the technologies we're developing to create long-term positive effects for the world. If you want sort of a 2-minute spiel about that, think about it this way. Consider China. About, let's say, a few hundred or about 1,000 years ago, and look at Europe. China's phenomenally well developed. They've developed bone china, ceramics, pottery, right? And they're really, really, really good at it. They ship it all over the world. The Europeans haven't. Their pottery technology is just not nearly as good. On the other hand, the Europeans develop some amount of ability at using glassware. So they've developed this ability to make glass. But glass is expensive. It's much more fragile than pottery. You can't really use it very easily. The glass you have nowadays is much stronger because it's got all these additives in it to make it a lot more powerful. But what ends up happening is it turns out that glass has a much deeper tech tree, if you've played any strategy games, than ceramics does. You develop pottery, but then you're stuck at pottery. But if you develop glasswork beyond a certain level, suddenly you're making telescopes and microscopes and 10 other things, and your scientific ability just leapfrogs ahead, right? Today, we're developing all of these technologies around the world, which we are sort of spreading across our planetary scale civilization. But we don't really understand these long-term effects yet. So we're looking at various technologies, trying to understand how things will affect us in sort of the 5-year, 10-year, 50-year, 100-year scales, and also looking deeply into the ethics of things, supply chains, and things like that. I can answer more questions about that if people want to talk right at the end. Now, courses are one thing, right? I can just teach one course and that's that. What's the big deal? It's not just courses, right? There's a lot of students who do interdisciplinary majors. You don't need to. You can do multiple majors. You can do a minor. You can do concentrations. And these are all definitions that say, you know, how many courses you need to take in particular areas and what the requirements are. But a lot of students end up doing this, right? A lot of people take, say, computer science plus economics and so on and so forth. Stuff that's normally not possible in India, but we do provide the freedom to do a lot of that. And especially, you know, Juice teaches this course called the Digital Humanities, which is fascinating. There's a lot of super interesting interdisciplinary courses because that's what makes you think. The problem is once you're stuck inside these silos that I study physics, I'm not a historian, I study anthropology, I'm not a computer scientist, etc., etc., etc. As long as you're stuck inside these silos, in some sense, you're competing against all the ancestors that came before you, right? Because those people were stuck inside those silos also. Once you step outside those, there's a lot of low-hanging fruit that you can then attack, because presumably the people before you who created these silos didn't do that, right? Now, I'm just going to tackle this question head on because I know a bunch of you are probably going to ask me about it sooner or later, which is Ashoka has this 3-year bachelor's plus 1 year, right, setup. And many of you are considering that versus a BTech degree. What is the difference? I can give you 2 generic differences. It's not. It really depends on where the BTech is, to be honest. Like if you provide specific things, I'm very politically incorrect and happy to talk about that. But generally speaking, when you're talking about a deployment of technology versus understanding the technology itself, these are 2 completely different things, right? Engineering is critical because without it, we wouldn't have any of these creations. But there's a difference between someone who designs the idea of an engine and who thinks about how to improve engines in general or how to make a car more crash-proof versus the person that puts the car together, right? And that's, again, different from the mechanic that keeps the car in shape. All of those people are important. I want to make sure I'm not sort of implying anything about sort of, oh, the dignity of this labor is less than that or something. Nothing of the sort. All of those processes are important, but they're 3 different processes. One, in sort of computer science terms, the scientist, the person thinking, designing the car, thinking about what the engine should look like, what kind of oil should go in, all of those details, that's the computer scientist, right? The person who's physically sort of putting the car together, making sure everything stays in place, putting the details together, so on and so forth. That's super important because there's a lot of ground level stuff that when one designed the engine, one didn't think about, right? That's the engineer, and that's super important also. Now, once the scientist has come up with certain ideas, the engineer can maybe produce 50 different cars. Now they can go ahead and design. But the scientist comes up with the core concepts that allow the engineer to design. Once the engineer has designed it, these can be maintained and recreated by other people. In computer science terms, these would just be the programmers, so to speak. So programming is actually a really, really small part of CS, right? So there's programming, there's engineering, and there's actually looking at the science of it. And these are different things. Technically, that's what should happen in a BSc versus a BTech. But in reality, it's some intermixture. BSc has more of the science, BTech has more of the engineering, more of the deployability. Although, to be honest, because it's computer science, it's super deployable stuff. A lot of our students end up sort of doing, or at least trying to do, startups and things like that. And some of them have been fairly successful. So yeah, that sort of thing. Happy to answer more about this later on. Now, I was asked to sort of mention some of these projects that are going on at Ashoka. I'm not going to go through everything because it's too much pain. But we have some really cool stuff. I'll just pick one of the next 3 slides. So I'll pick one from this slide, one from the next one, and one from the one after that. From this slide, I'll just pick the covalent magnetic tweezers thing. That's actually a fantastic piece of work we're doing in collaboration with the biology department at Ashoka. We actually have, is it the only one? So there's something called a single molecule lab. And it is what it sounds like, right? It's essentially the idea of having some kind of setup where you can manipulate individual molecules. And I'm pretty sure ours is one of like 5 in the world, definitely the only one in Asia. And what we're looking at is using magnetic forces to manipulate proteins, right? So there's, let me take a step back. You know that diagram of the cell that you were taught in school? Mitochondria is a powerhouse of the cell. Yeah, that's completely wrong. It's sort of like the picture of the atom you were initially taught. It's garbage. In reality, a cell is much more complex than that. And the way a cell moves around is like sort of like this blind entity that has all these tentacles and just sort of feels its way across. It has all of these tentacles that reach through the cell wall and it's just sort of feeling its way around. And these tentacles are made up of proteins. In human cells, we're talking about talin, integrin, and so on. And what's amazing about these proteins is they act essentially like mechanical computers, right? If you've seen these old Tom and Jerry cartoons, you know the ones where there's like this collapsible gate-like thing and it's got a punch at the end of it, like a punching glove, and it goes like boing and then hits someone and comes back. That's what these tentacles actually look like. And depending on what they attach to, they change. So this punch goes and click and says, oh, I found a liver cell, and goes cut. And so some part, it undergoes a conformational change. And so each part of that protein assumes a different conformation. And depending upon that, you can fit in different things. Why did I say all of this? Well, it turns out that when you're doing this in a lab, you're trying to figure out whether a particular medicine will work in a particular way to change how a protein behaves. Let's say you're trying to inoculate someone against COVID or something. I don't know why you'd want to do that, but anyway, you would want to do that. The problem is because this protein can take 10,000 different conformations, you're just dealing with this basic protein. You need to sort of stretch it out the right amount to have these other things fit in, because otherwise they won't react. It's not like a standard chemical where it's always the same shape, so it always reacts. You need to stretch and squeeze it so it reacts under those conditions. You have to test it out under force. And we basically use magnetic systems to stretch and squeeze these proteins in various ways. So the computer science department, we're actually helping build these devices. And we're also running a bunch of this AI stuff to reduce the number of experiments they have to do. Basically, if you do 10 experiments, we say, okay, do this one next, and I can simulate the results of 10 other experiments and so on. Let's see what I want to hit in this slide. I want to hit fairness in AI. I think that's important. So we're using AI all over everything. It's become kind of pervasive. You probably don't even notice it, right? So let's say you want to get insurance. There's plenty of insurance companies or bank loan companies that have an AI scoring system that just tells them, this person is a red, don't give this person a loan, and so on and so forth. And the problem with that is a lot of that depends on old data. So let's say you're in New York, you get in jail, whether you can get bail or now depends on an AI system called Compass. And there's a lot of data that shows that it's, the AI itself is very racist. And that's basically because the data that was fed to it was also racist. So how do we determine whether AI systems are fair or not? How do we test these systems for fairness? And there's a lot of fascinating work in an area, unfortunately, called FAT, stands for Fairness, Accountability, Transparency. We have some incredible results looking at explainable AI from there. So what you wanted to do is not just say, put this person in jail. You wanted to say, put this person in jail because of blah, 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 blah. Similarly, if you have a facial recognition AI, if it says these two faces are different, you don't just want it to say these two faces are different. You want it to say these two faces are different because this person has a bigger nose than that person, the forehead's a different shape, and so on, right? You want that explainability because that helps humans interact with the system and also correct errors, because what if those two are the same? Now you tell them, no, the forehead's not a different shape, actually, right? And we actually have some really nice papers about this that we're in the process of submitting. This is me. This is what I do. My main area is cryptography. I do a lot of work in privacy-preserving technologies, which is making sure that if you have data and I have data and we both need to use that data, we can't just lock it away. We can both use that data without giving it away to anybody. And that has a lot of interesting stuff with it. I do a lot of other things. I'm especially interested in sort of real world interactions with technology. And I've started doing a lot of work looking at how the technology that we develop is actually used in society and sort of the ethical implications thereof, and how humans deal with technology at a cognitive level. And that in itself is a whole field, of course. But there's if people are interested, I'm happy to talk about sort of the cognitive science side of things. Now, when we're talking about how things are affected at an ethical level, I mean, sure, it's cool if a professor just kind of thinks about it. But at an institutional level, we do a lot of AI for social good, right? We have this Trivedi Political Data Center, which looks at a lot of interesting stuff, processes a lot of data in terms of, let's say, for example, what kinds of people make what kinds of arguments when talking in parliament, right? Who actually supports minority rights instead of just signaling it, and so on and so forth. And they do deep research looking into that kind of thing. That last one, Ramses, that's actually something I'd been working on. A lot of people have a lot of opinions about reservation policies in India. The way I look at it, I have a different issue. My issue is Group X has 7% reservation. Why is that a whole number? Yeah, you can tell I'm a mathematically inclined person. I'm just like, wait, why are all of these reservations always like exact round numbers? Why isn't it 6.381? Because if you're trying to overcome disadvantage, I mean, there's no reason why disadvantage should be measured in round numbers. And the reason is, of course, that these are politically arrived at. These are not data-driven in any reasonable way. So if you actually had to measure disadvantage, and especially the intersectionality of disadvantage, think about two people with a hearing disability. One is a male from a rich family, and the other is a female from a very poor family in a backward district, right? And they both score 85% in an exam, right? The problem is right now, both of their reservations or quotas or whatever you want to call them, they're going to be the disability quota from their hearing disability, right? It's the smallest pool where they can compete, so they'll both go for that. While in reality, one person's disadvantage is significantly greater than the others, right? You can have other cases as well. Well, I won't spend too much time talking about this, but the idea is, how do you actually measure somebody's disadvantage? And we've come up with some really nice data-driven frameworks for doing that. So it's not just sort of Debian says this person is more disadvantaged than that person. Actual real data-driven systems. These aren't perfect. They don't obviously look into cultural capital and 10 other things, but it's a start, and it's certainly better than political winds driving these numbers. Now, because of Ashoka's location, we're around Delhi. Not the best thing right now, but we're in the NCR area. And what that means is we very often have the ability to hold a lot of events, right? We do a lot of workshops, we do a lot of conferences and stuff like that. And we bring in really, really good people. So, even if you don't come to Ashoka as a student, an open invitation, come attend some of these workshops. They're really going to be worth your time if you're in the Delhi area. Specifically, I said towards the end that I wanted to talk a little bit about computation directly. And this is something that we're doing in the CS department right now. There's a company, Emphasis, which has very generously founded this applied computing lab, where we're attacking a lot of very, very, very difficult problems, looking at rational drug design systems. By the way, so like the last antibiotic that was developed, sort of our newest one, that was developed by a team, I think, out of Britain and France. But they developed it entirely using AI. Like, it wasn't done by chemists, it was done by artificial intelligence. They told the system what they wanted, and it built it over time. So we're looking into systems like that. We're doing a lot of work in explainable AI systems, trying to understand things like, oh, given an image, can you explain what's going on there? This is a girl at a table with her hand on her chin. Can you actually derive that meaning from that image? And we've done some fascinating work in that area. And I'm happy to talk about any of these sub areas should people have questions. Now, a lot of what I said till sort of up to this point has been about sort of large scale things, big companies, big research, that sort of thing. One might imagine this is sort of PhD students and upper year undergrads only doing this stuff. That's absolutely not the case. We have a lot of students who, after doing the coursework that I mentioned, the double majors especially, they produce really high quality research. I couldn't fit in more than 5, but, and I'm not putting the details of the papers out here, but we have a lot of students who are, in fact, actually, I don't think any of the new first years still have any published papers, but second, third, fourth year students who've published papers at really top-notch venues. I'm not talking about, okay, not being racist, but like some sort of fake Indian conference. No, I'm not talking about that. Like proper top-notch international venues and producing real high-quality research, right? This physics plus AI thing that I mentioned is actually an attempt at attacking the three-body problem from physics. And we're using some really cool machine learning approaches to try and do short-term approximations and things like that. The Neuro plus CS stuff is also fascinating. It looks at, all of us use passwords for all sorts of things, but how can we create neural processes that produce high-quality passwords? Simple way to think about it is, if I ask you to write down 10 random numbers, whatever you write down is going to be really, really bad, right? Because humans are not good at randomization. There'll be all kinds of patterns in the numbers that you write. And instead of 10, if I tell you to write down 100 random numbers, then it'll be incredibly bad. But what if I can come up with a process where I say, okay, I give you a seed, a starting point, just like you would give to a computer system. And now I want you to, I give you a method to turn that into a shape in your head, or a smell, or a set of colors, and I give you techniques to manipulate that, and you produce random numbers by reading off of that system. And we've actually come up with we're working on, but this is already something that's been published, but we're doing more work on it, coming up with ways for individuals to come up to use these techniques so they can produce really complicated passwords with minimum mental sort of pressure. Because the way we do passwords now is like, oh, it has to have capital letters and like small letters and like special symbols and can't start with it. It's like, come on, who's going to deal with all of that? And we just use the same password everywhere, but like #1, #2, or like dollar or whatever. And that's not a good way. So we're doing a lot of work there, and we've made some very nice progress. And like I said, like actually publishing in top-notch international conferences and journals. Having done this, you know, I've come down the whole way, right? I've talked about computer science in general, then I went into research, then I went into what undergrads are doing. The next natural step that this conversation goes to is, okay, you told me about what undergrads are doing. What happens after? And I would love to tell you what kinds of jobs you'll end up pursuing should you do an undergraduate at Ashoka or whatever university. And I'm sorry to say I can't. And the reason I can't is, you see this list? This is the list of the top entry-level, highest-paying jobs for computer science bachelor's degree holders. This is worldwide, right? If you'd asked me 5 years ago, I would have guaranteed you without thinking twice that artificial intelligence engineer or something of that sort, something with the word AI in it, would have been in the top 5. It's not even in the top 10, right? Unfortunately, or fortunately, computer science as a field is moving so fast that many of these jobs, HCI specialists, cloud computing specialists looking at load balancing and things like that, cyber risk man, these were not jobs that people had even heard of 10 years ago or 15 years ago. And as I said, even 5 years ago, I would have not guessed this list correctly. So given that history, I can't tell you that by the time you graduate, and more importantly, 10 years after you graduate, what the jobs in your area that are sort of high paying and lucrative are going to be. And if someone else tells you that they can, they're lying to you. No one can. Now, this is something that people have actually figured out, right? And you can see this by looking at current people in industry who are young. So people who have just been working for, let's say, 5 years or 10 years, sort of starting out in the industry. And if you go back in time, if you ask people to guess what will be the most important thing for people, a lot of people would guess things like cash bonuses or healthcare and so on, or pension schemes. These were the things that were important to people a few decades ago. When surveyed, however, and this is not one country, this is across 75 countries, and it's many thousands of people who were surveyed, training and development was by far the top option, and flexible working hours. And why is that? Well, there's no point joining a company and doing some kind of coding work if you're going to be thrown out after 5 years. It's completely useless. You earn some money, but then you get tossed out, and you have added no value to yourself. Unless you can look back at yourself and say that, okay, I can do stuff now that I couldn't do 5 years ago, it's a matter of time before you get sacked. Because think of it this way, you've learned a particular, let's say, computer language, you've graduated, you're going to work at a company, and every 2-3 years you get a raise. 10 years later, your company realizes, wait, why should I pay this person so much money? I could hire a new 22-year-old who'll work for like half the price and who knows the newer computing languages. So you need to continuously be in training and development to sort of keep yourself employable. And that's incredibly important. And this is something that a lot of people, you can actually see this when you survey people who are in the industry. Given industry stuff, our students do quite well. Lots of people in lots of different places. I didn't even add the people who'd gone on to sort of various universities. I write a lot of letters of recommendation, so I know that many of them have gotten into sort of top, usual top universities across the world. So cool stuff happening there. And yeah, we have people working at amazing places doing great work. That's it for me for today. End of my slideshow. So if you have any questions, I'd be delighted to answer them.
So yeah, we have quite a few questions, Professor. So I'm just going to start off with the ones that are most frequent. So the first question I see here is, what are the prerequisites for CS at Ashoka? If someone stopped studying CS at during their class 10th, could they still major in CS?
Right. I think you need math. And I'll defer. The Ashoka website has all these details in the computer science department webpage. But from what I recall offhand, you do need math. CS is not required. You can we teach CS from scratch. But the problem is, unless you have that a little bit of mathematical background, it's really difficult to start from scratch. But a lot of my students end up doing sort of not majoring in CS, because you don't you don't enter Ashoka saying you're sort of with a CS major, right? You declare your major afterwards. So a lot of people end up doing some CS classes, which ends up making whatever other work they do a lot better, hopefully at least.
Okay, so so another question that I see here is that if someone is interested in pursuing another field such as biology or economics, how can CS help them in their field?
I mean, I think I described the bio stuff. I'm working on a lot of bio stuff right now, for example, right? It's not just that project. I'm working on with another professor, Gautam Menon. I'm working on this giant Gates Foundation thing on simulating COVID in India, essentially. And that's sort of epidemiology in some sense, but literally, if you've again played any strategy games, yes, I used to play a lot of strategy games. But if you've played any strategy games, it's like simulating an entire sort of population with 1.3 billion agents moving around. And instead of trying to make guesses and stuff, we just simulate the darn thing and see how the disease spreads. So lots of stuff there. Economics, like that Ramsey's work about reservation, that's pure econ at the end of the day. We're using computational tools and actually a lot of AI to do that. But I mean, you could do that with regressions. You just not get very good results because the system's not linear.
All right. So as you rightly guessed, multiple people have asked about differences between a BSc and a BTech degree. But specifically, what I'm seeing here is that they're asking, um, does Ashoka CS cover all the courses taught typically in an engineering degree? And in terms of jobs and internship opportunities, how would Ashoka CS be different?
Sure. So things you got to know about this. Number one, Ashoka CS is a relatively small department. That means it's very focused, right? If you're trying to compare it to a BTech, let's say at IIT Bombay or something, it's a much larger department, many more electives. On the other hand, what you won't have at, let's say, an IIT Bombay or Delhi, for example, you will not have the ability to do any of this cross-disciplinary stuff, which we end up doing a lot of, right? In terms of course coverage, I think we do cover pretty, I mean, of course, otherwise we wouldn't offer a basic bachelor's degree. So we cover all of the essential course requirements. But I think we also have a lot of other courses like this digital humanities thing and so on and so forth. We actually have top-notch people from the humanities collaborating with CS professors and CSTAs in many cases to teach these kinds of courses. And that's not something you'd find at the average engineering college, or actually even the best ones in India, to be honest.
Right. Another question I see here is, how important is math to take up a CS major at Ashoka?
I mean, you got to have it.
Yeah. Okay. There's a question about undergraduates doing research. What is the extent of undergraduates doing research? And then what is the ASP? Why should one opt for it? And what are the research opportunities during ASP?
Sure. Undergraduates doing research. All the papers I talked about, those were only undergraduate papers, right? I have PhD students. I didn't list their papers there, right? So this is all undergraduate research. We've had, my group alone has had, I think, 5 or 6 undergraduate publications in the last year, in the last 12 months. So, and not trash publications, like proper ones. So yes, a lot of people do undergraduate research. People start early. People start approaching me, usually even in their first year. And by the time they're in sort of their second year, many people are ready to submit stuff. Some people have already published stuff by the time they're in their second year, which I certainly hadn't done. So definitely. What was the second part after undergraduate research, the ASP thing?
Right. So what is the ASP? Why should one opt for it? And what are the research opportunities
Sure.
during
So I
it?
think to have a solid understanding of any subject, you need that 4-year degree. There's a reason the US does the 4-year degree thing. We inherited the 3-year thing from the British and haven't really grown past it. I think, at least this is the way I was. When I was going into college, I didn't know what I wanted to do. I took computer science because it was a subject I hated least. And because you don't know what to do, well, obviously you haven't had the exposure. You need to get that exposure, right? You need to take a bunch of classes. Ashoka has these systems of foundation courses, which you have to take in various areas. So you spend a lot of time in your early years at Ashoka taking these foundation courses. Or if you're lackadaisical, you miss them and have to take them right at the end in order to graduate. But like, you usually end up taking these courses super early, and that gives you this necessary exposure. And then you declare your major and start learning more. Just because you thought you were going to major in chemistry doesn't mean you can't switch to computer science or physics or anthropology or like, I don't know, whatever else. Because of this, you need that 4th year because you're spending this extra time exploring. This is separate from all of the labels, right? I think doing that 4th year is really, really good for you because that then gives you this extra jump, this extra ability, because you end up doing a lot more research during that 4th year. A lot of the students who stayed for their 4th year end up either publishing papers or, especially we have these capstone projects and theses, doing some really high quality work. And especially in computer science, that can help build your portfolio. Like, it's one thing to say, okay, I did all these classes and I performed well in them. It's another thing to say, look, I actually built this gigantic high quality system, right? And the ASP gives you the tools and the time required to do that.
Okay, so does Ashoka have placement sessions like typical engineering colleges? And if so, how are they? And if not, then how do Ashoka students find themselves at the likes of firms like Microsoft and Google, as we see on the Ashoka website?
I mean, we have an office that looks at that stuff. I personally, with a lot of computer science students, I run this thing where I help them reach out to different companies. And we have a lot of good relationships with these companies, right? And so it's not a standard sort of, I mean, we have some amount of campusing, but even more than that, because we're relatively small in size, right? We actually have an office that reaches out to these companies and gets students interviews and so on and so forth. It's not a sort of campus fair-like thing.
Okay, so please tell us more about the new machine learning lab at Ashoka, the emphasis lab.
Sure. I don't know, that's a super open-ended question, but I'll say 2 or 3 things. Number one, a lot of people have done a lot of good and bad stuff with AI, right? Computing in general. You know, there's some people that are looking at combating climate change by trying to figure out, using satellite imagery, what areas of forests should be conserved. Simultaneously, there are other people who are using it to oppress. There are other people using it to have guns that auto-target people, and so on and so forth, right? So I think having these centers for social good, applying the technologies that we've built in order to improve humanity, is something that's really critical. At this particular center, we have a set of problems that we try and attack. One is chemical, looking at trying to find new ways of synthesizing and structuring chemicals. And that turns out to be super important, especially if you care about climate change. And this may seem weird because, I had been talking about medicine. Yes, that's there. But something like 20-25% of heat emissions of your carbon footprint, of humanity's carbon footprint, is actually chemical processes. There's no point having solar energy or whatever if you can't produce steel. There's a chemical process required to do that, and that produces a huge carbon footprint. And we're actually looking at lots of different ways, not just to design drugs, but also to improve these chemical processes, these chemical pipelines. That's just one problem. We're looking at how to help, say, blind people navigate the world. So, you can have a camera that constantly reads out what's in front of you. You can take a note and it tells you what the value of that banknote is, and so on and so forth. That's what we're using, that image to text system that we were talking about. And it's gotten pretty good in terms of explainable AI systems. I mean, there's a lot of different applications there.
Okay. Does Ashoka have a healthy coding culture or a developing coding culture that's seen in engineering colleges? For example, hackathons, etc.
Yeah, we have I'm in the middle of organizing like 2 of them. But yeah, we have. I mean, this is something that the answer to that will change every year, right? Because Ashoka is such a young university. But we're having 2 hackathons over the next few months. There's one, a general one, and there's one being organized by the Women in Computer Science group, and so on. So yeah, like we do a lot of that stuff. Now, whether the culture is healthy or not, that's something Archit is probably going to be better at answering than I am.
Okay. So would a BSc or an advanced major in CS from Ashoka be accepted for a master's at a top university in the UK or US?
So it depends, right? I can tell you that people with bachelor's and ASP degrees, depending on whether you're looking at a 3-year or 4-year degree, US requires 4 years. I've had plenty of students go on to do masters and PhDs with that 4 years of education. So that's definitely accepted. In the UK as well, yes. The reason I said that's going to depend is because certain universities have these, technically they'll say yes, but in reality they have lists of places where they take people from, where they have alumni from, and so on. And that requires time and name recognition. But technically speaking, yes, you'll get in wherever.
Okay, so how does Ashoka alter its curriculum to give you a liberal arts experience as opposed to an engineering degree? Basically, what's the curriculum difference?
Basically, what is liberal arts, right? So I think there's a problem in translation, because liberal arts basically came from liberalis ars and so on. Like, we don't really learn Latin, which is a good thing. But liberal arts has nothing to do with the arts as such. Okay, the top universities in the world, Harvard, Stanford, MIT, Yale, whatever, those are all liberal arts colleges. You get liberal arts degrees from all of those places. And it is a particular way of looking at the world, right? I'm going to be somewhat politically incorrect here and say that, look, there's a reason why Indian universities, despite being so, the professors at all of the IITs are phenomenal people, right? These people aren't idiots, right? They're at the bleeding edge of their fields. Why isn't there a single IIT in the top 100 of any ranking you can think of, right? Ashoka is a new university. It's not even eligible for some of these rankings, but whatever. But the IITs have been around for a while, and there's a reason why they haven't been able to break in. It's because they're still stuck in this age-old engineering curriculum way of looking at things, right? You need that unsiloed approach. You need that fresh way of looking at the world. Otherwise, as I said, you're constantly competing with your ancestors, which is just an absolutely terrible idea. If you're only looking at things from that deployability engineering level, or you remember the car example I gave you, you need to be at the scientist level of thought. And this is not a hierarchy, right? It's not as if the scientist is better than the engineer. They are just different. And you need to be at the scientist group in order to be able to do a lot of this stuff. What the liberal arts allows you to do is have a broad-based view of the world, right? I mean, there's people who'll give you stuff saying EQ and all of that. Yeah, sure. All of that's there. But even more than that, having just sort of coding expertise or engineering expertise in a single area, you'll turn into someone who gets a reasonable salary in some place. You will never be the person that founds a big company, right? With low probability anyway, right? And the reason for that is you need that broad-based, full, big picture view of the world, which you won't get otherwise. And the problem with a lot of universities in India is they rely on students to gain this knowledge sort of by themselves. It's like you're relying on students to talk to their dorm mates and then found the company. It's never sort of directly because of something that happened at the university, or rarely so. If you look at universities, especially in the US, they've gotten really good at breaking these silos and sort of churning out, let's say, in a cohort of 50 students, 10 companies per year. And out of those 10, maybe 5 end up succeeding and doing really well.
So someone in the Q&A asked that they have a BTech in computer science and engineering, and could they pursue a PhD in CS from Ashoka?
Yes.
Okay.
That was an easy question.
Yeah. Someone asked if you could describe the difference between cryptography and cryptocurrency.
Oh, wow. I don't know where to say. Those are completely different things. It's like, what's the difference between the capital of Japan and the concept of waterfalls? So cryptography it refers to a class of techniques that you can use to hide and manipulate information and to control who can read it, who can understand what's hidden inside, so to speak. Cryptocurrencies happen to be one particular usage or adaptation of that technology in order to create a virtual currency system, right? So, I mean, cryptocurrencies and these are basically ledgers. These are sort of accounting books. Computation, modern computational techniques have allowed these accounting books to become distributed. A bunch of people can keep them, and to have certain guarantees that random people can't go in and edit them.
Okay. So there's a question in the Q&A asking me about my experience at Ashoka. So I'm just going to tie in a couple of questions. I'm going to answer the hackathon question as well about the coding culture. So basically, at an engineering college, all you would be talking about to your peers is about tech. But at Ashoka, when you talk to your peers, they're studying history, they're studying literature. So your conversations are going to be about various different things, rather than just tech. So that adds another dimension to your personality, and I think that has been really beneficial for me. At the same time, I don't think there was any compromise on the rigor of the technical parts of CS at Ashoka. So I think I got the best of both worlds at Ashoka. That's what I would like to say. And with that, I think we are approaching the end of the session. So thank you, Professor. I hope that the webinar has been helpful in understanding the uniqueness of the CS program at Ashoka. Few last points before we wrap up today's session. Please take a minute to share your feedback with us. The link to the feedback form is provided in the chat box. Our next webinar is scheduled for Friday, 29th January from 6 to 7 p.m. on Learning Support at Ashoka University with Reena Gupta, Director, Office of Learning Support. The Office of Learning Support at Ashoka University promotes an inclusive environment for students with disabilities or other neurodiverse needs. Through an interactive process, we are a support system to help students with specific needs achieve their individual academic goals. The registration link for this webinar is provided in the chat box. We would also like to invite you for the upcoming webinar, Why Study Science at Ashoka, with Professor L.S. Shashidhara, who is the Dean of Research and Professor of Biology at Ashoka. This webinar is scheduled for Tuesday, 2nd February at 6 p.m. The registration link to join the session is provided in the chat box. Lastly, I would like to inform our audience that round 3 applications for the undergraduate program are open now. The last date to submit your application in this round is 14th March 2021. You can start your application at apply.ashoka.edu.in. Please visit our website www.ashoka.edu.in for complete details on the admissions process and timeline. If you have any further queries or would like to know more about Ashoka's unique interdisciplinary undergraduate program, you can write to us at apply@ashoka.edu.in or call us on the number provided on the screen. Thank you and take care, everyone.